For those of you who don't know Anil, I don't think there's. I mean, there's only. If you look at the book, there's 3 authors, but there are. Rarely are there individuals who care so much about not only the evolution of a language, but about like just technology in such a way that's true. I mean, this is the problem I think that as tech is becoming such a popular place to work, that it sort of seems like it's growing bigger, and yet it's rare that we find people who are true to its very roots. And I think Anil's definitely one of those individuals. He's helped us out a lot. I mean, when we just asked, like, hey, Anil, could you help us find individuals who could work with us, or could you help us let's just talk about Esper? What do you think about it? It's an idiotic idea. He's always been willing to do that. So without further ado, I'll stop talking. I'm excited to go and welcome Anil to our very first OCaml Later.
Thank you. Well, I'm excited to be here. Actually, I've known Martin for a very long time, and we use tons of his code in everything we do, so it's a real privilege to actually show up at Esper. So does everyone here know OCaml? Just for a start. Perfect. This is good. Okay, but about 80% of the room. Cheryl back there. I'll teach you OCaml soon. And then, so I wanted to just spend a little bit of time talking about this Unikernels movement that has been taking off recently. And I wanted to make this really interactive. So I didn't want to spend a lot of time in slideware, but I figured it would be good just to give you a really quick introduction to what unikernels are and what the point of them is, and then just dive straight into a terminal and show you a bunch of examples and just figure out exactly what you need to do to get started by using them. If at any point of these examples and so on, just feel free to just shout out and keep it interactive so that if you don't understand something, if you want to know something more about a tool, you should be able to understand exactly how this stuff works for yourself. So part of this is this effort called MirageOS. And in about 2011, we wanted to start building safer infrastructure for the cloud. And even back then, with Zen taking off quite a lot, Amazon had a lot of capacity on EC2, and we're sticking all these virtual machines everywhere, and it's clear that there was a disaster in the making. So MirageOS is an effort to write code in a high-level language and just output a very, very specialized little kernel that does exactly what you described in your high-level code and put the minimum amount of support in for anything else. So everything here is actually self-hosted. So I was showing a bunch of people just before the talk started that it's actually hosted on one of these QB boards. I'll explain how that works. And it's got no external dependencies. So the website is completely standalone, no disk devices or anything, because everything is crunched into it. It's taking all the JPEGs and stuff, embedded into the OCaml binary, shaking it around in the OCaml compiler, and just output a standalone kernel. And it's actually reasonably high level. So as we've been building out the unikernel prototype, we've got more and more high-level libraries. Things like CoHTTP is using Martin's YoJSON, for example, for the web support. And the end result is that you just have to give it a bunch of static HTML files, and it outputs a unikernel. And I'll show you how that works. And the stuff I'm going to show you is extremely bleeding edge. I figured I'd show you our new safe TLS stack. We just got it working this morning. Thomas Casinier just sent me a pull request about an hour before we got in the car here. So it might or might not work. But if not, we'll debug it together, and we'll figure out how to make it work. Because the idea is I want to put it live here in the talklet. And one very, very cool thing that came out of this is that the binaries for this whole thing are small enough to track in Git. So I'll show you how that works as well. It's pretty nice that you can take a unikernel and you can track your infrastructure in Git on GitHub. And we've been doing it for about 3 years, and GitHub hasn't noticed yet. So we have some pretty big repositories, but it's kind of incredible that we can just go back in time for 3 years and see exactly what went into the infrastructure that built it. And all of this is using standard OCaml tools that we've been helping to develop and maintain. So things like OPAM. How many people here use OPAM or have used it in the past? Oh, that's fantastic. So OPAM is an OCaml package manager written originally by Thomas Casinier, who's one of the MirageOS core developers, and now maintained by OCaml Pro, our colleagues in Paris. And we're using it everywhere in MirageOS to make this stuff work nicely. So the unikernel approach can be summarized very, very simply. The thing we want in the cloud is just a specialized virtual machine image. And it used to be in the past that we had operating systems that existed to support many applications, right? Big multi-user applications. And the C shift when the cloud happened is that we have these applications we want to run, and we just want to assemble the minimum amount of operating system support required to support those applications. If you have MySQL, you don't need to have a massive graphics driver and OpenGL subsystem. If you're running a web server, you don't necessarily need complicated buffer caches and so on. You just want to take a more artisanal approach and just pick the right libraries you need to pull that off. And in return for doing this, in return for not requiring a full operating system, you get a ton of benefits. And this is really what's driven us to continue building all of this clean slate code as the years have gone by. And in particular, they're incredibly self-contained. By definition, the unikernels have nothing in there that introduces an external dependency unless it's specifically installed. So unlike a normal OS distribution where there's maybe a ton of subtle third-party dependencies, in this one, nothing that isn't compiled in there will be present in there. And they're very compact. I mentioned they're very small as well. Now, the nice thing about this is that you're essentially taking the embedded systems approach and sticking it onto the cloud. So whereas it's been quite easy to allocate virtual machines with gigabytes of RAM, you're ultimately paying for these things. So with the embedded approach, without doing any extra work, you're just compiling all the code you need and just putting it on the cloud. So we've actually run tens of thousands of these unikernels on a single Zen host. And in fact, even on these ARM devices, we can run, I think, about 30 or 40. So it is just more efficient because of the lack of all of the other bits that it doesn't need. And one of the neat things is that it's seriously portable. So OCaml has never been it's always been a very Unixy language, but when writing code in this style, it's very, very portable. So you can not only compile it to Zen, which is obviously no operating system. We've just started compiling to JavaScript. So the database I'll show you runs in the browser and maps its storage interfaces to browser subsystems. And there's quite a viable big to-do application as well that Thomas Leonard, who's one of the core team, has written as well. So the basic way it works is that you want to take an operating system, and this operating system has loads of layers, and it's got a whole bunch of kernel stuff going on, and it's got the language runtime, in this case OCaml. Then you've got your application binary, and then you've got your config files. So with Mirage, instead of just bundling these up together, as you might do, for example, in a Linux container, you take the whole thing, you run it through the Mirage compiler, and in this world, the config files are normal OCaml values, and this is your source code, and everything is compiled in. Now, the sea change is that all of these kernel subsystems just become libraries. So they become normal OCaml libraries that implement device drivers or schedulers or some other aspect of your operating system. So instead of having an operating system that cocoons you, it's turned into what's known as a library operating system, where your application links against operating system functionality and can only do one thing. Now, library operating systems have traditionally not been very useful because they're not multi-user. So in my research group in Cambridge, before Zen, the previous operating system was one called Nemesis, and MIT built something called the exokernel. And the problem with these is that whenever you built these library operating systems on bare metal, they bit rot very quickly because you need to rewrite all your device drivers for this particular new operating system. So when Zen came along, Zen took kind of the good bits of Nemesis and turned it into a hypervisor. And suddenly we have this widely deployed virtual hardware interface that does the minimum required to support disk drivers and network drivers. So when you launch something on Amazon, you're running on top of Zen, but then you're layering all of the old software stacks on top of that. So suddenly it became viable to rebuild cool new operating systems because we only have to support one hardware base. So everything just runs on top of Zen and implements through libraries these little device drivers. And then the ultimate result is a unikernel. And the cost, if you want to reconfigure this thing, you're out of luck. The only interface to reconfigure is by recompiling the whole lot, and it'll respecialize and redo everything it needs to do to put out a unikernel. But of course, in the cloud, that's pretty much what you do anyway. It's easier often to destroy a virtual machine and reconstruct it, even if you're using Puppet or Chef or something similar. So let me just dive in and show you now. Am I blocking the screen for anyone? Let me just, reconnect this thing. So here we have a simple console application. And I'm going to show you some OCaml. So what I'm going to do here is I have a unikernel. And this unikernel is very, very simple. It just says, given a start function. I wonder how I can, given a start function, just count from 0 to 4 and print hello world. Now, this is a pretty standard OCaml LWT function with one exception. We've wrapped it around this functor, which says that I'm in a main module, and I need you to give me a console. And so I'm not assuming that I have an OS console. I'm just saying, just provide me with an abstract console. And then given that console, I will then run my normal application logic and log hello world 4 times. And I'll use this os.time.sleep function. So I can just take this thing and say Mirage configure ---- Unix. And this just generates, first of all, it checks that, looks at the configuration file. It invokes the OCaml package manager to make sure that everything I need is installed. So in this case, it's checking for external dependencies, M4, for example. It's running the OCaml install for the various libraries required, in this case, the console and Unix. And it generates something called main.ml. And if I type in make, this is a normal Unix binary. There's been no magic here. And this just generates a Unix binary that I can run that does the obvious. It prints hello world. So now I want to say, given this portable yet useless application, I want to recompile it and make it run into Zen. So all I have to do is reconfigure the application. So I've now done Mirage configure --Zen, and it's gone through pretty much the same process, except it's installed a bunch of drivers that we haven't seen before. So it's installed Mirage Zen and a bunch of device drivers that implement Zen. And again, I just type in make. And this time, it's gone through the normal OCaml compiler, but it didn't stop. Instead of just outputting an ELF binary for Unix, it just kept going and linked in all of the Zen console drivers and so on that are necessary. So what's happened here is that at the end of it, it's actually built a kernel. And so this kernel, Mirage console.zen, with debug symbols and so on, is about 3.8 megabytes uncompressed. When you strip down symbols and you do dead code elimination, we can get that down to hundreds of kilobytes. So I can then run this by using Zen. So I can say xl create -c console.xl. So what's happened here is that it's now just booted as an operating system, and it's just printing out hello world. So this general philosophy of saying that we just want to write normal OCaml code, but anytime you need an operating system dependency, you parameterize across it. And then this just lets you say that I will supply the right device drivers and make this thing assemble together in the configuration that you want. And so the Mirage tool is pretty flexible. When I do Mirage configure, say, --Unix, what it's doing is that it's figuring out your hardware configuration that you want. It's looking at the set of device drivers you want, and it's generating a main.ml that has all of the right device drivers assembled together. So in this case, the Mirage tool has said, well, I need a console, so I will give you a Unix console. I will then connect the console up, which in Unix doesn't do much. But you could imagine that a more sophisticated Unix backend would attach to a logging service, Impala or whatever, or syslog. It's then saying, well, given this console that we've just connected, take my Unikernel and apply console to it, and have a module that is concretely applied. And then it's just saying it's go execute it and run the actual console command. It's pretty straightforward. When I do Mirage configure --Zen, it's doing much the same thing, except it generates a different main.ml. And this main.ml is very similar, except you can see it's attaching to a console Zen. Console Zen is a much more sophisticated module. It implements console device drivers, shared memory devices, everything needed to actually write to a bare metal console. But as a user, you don't care. You're just writing to an abstract console API. So why don't we do something a little bit more sophisticated? I haven't checked if this one works for a while, but let's see. So if I want to do a static website, when I do a static website, I have an htdocs directory. This htdocs directory is all right, here we go. So why don't we just say even more exciting? And I can simply configure this one up now as a Zen unikernel. And this one does a lot more, because obviously it has more than just a console driver. It's got a full networking stack. When you have a full networking stack, you can see that the number of packages being installed is dramatically higher. We have things like HTTP drivers, network drivers for Zen. We have the platform driver. And we also have familiar ones that you might see. For example, a regular expression library for HTTP. Things like Conduit, which is a network stack API. And all of these are installed together as normal OCaml libraries. And there's also this crunch command. And what this does is that given the static files that we were putting together, it just outputs an OCaml file which represents all of that content, which in this case is obviously very trivial. It's just saying that the MD5 hash of the hello Esper is becoming a normal OCaml module. So this works great for configuration files and so on. So now if we try to build this thing, it's going through the normal process, except it's linking in more libraries. And it's output for us a unikernel that if I give it a, so in this case, I will give it a network driver, zenbr not. And we don't need this much RAM. Let's give it 32 megabytes of RAM. We can drop that even further, most likely. And I can then now create it did work. Excellent. Now, what's happened here is that this unikernel is now gone over through DHCP, and it's running on 10.11.79. And so I can do curl 10.11.79, and there we go. We've got a web server up and running. So this one is a bit more sophisticated, but the unikernel that we wrote is actually not that bad. So it's just a normal unikernel, normal bits of OCaml code where we have HTTP, we have a bit of file system work, we do some work on URI munging and so on, and we have HTTP callbacks. This is code that you would write in a normal web server in OCaml. The difference is that if you look a little bit higher, we've just added more parameters to our universe in our module signatures. We've said, we need a console to log, but I also need a read-only key value store. That's a file system. And we also need a co-HTTP, which is the web server that we use. We need that to be supplied as well. And this is abstract enough that we can actually compile this web server in many, many modes. So I can compile it as a Unix socket library. I can compile it as a TUNTAP library running on Unix. And I can compile it as a Zen unikernel. And the right ones are assembled and pulled together. So the question is, how do you control all of these configurations, right? We've already seen that we can have 3 combinations for a simple web server. And you can imagine JavaScript, for example, we can compile to Node.js or whatever. There's many, many ways we can take this code and make it executable. So what we did was we built a little domain-specific language that defines a configuration. And what that does is this. You take a config.ml, and this config.ml is executed at build time. So whenever you run Mirage configure, it just goes through this config.ml and it just executes the code, and that gives it a set of device drivers that we'll actually use to make this executable. And this means you can write very sophisticated build scripts that are just written in normal OCaml that decide based on environment variables or config files exactly what hardware optimizations and permutations you want. In this case, we can decide, do we use an external file system? Do we use something crunched into it, into itself? So if you have a huge web server, it can attach a FAT or ext-based file system. If you set the network device interfaces, it will do one thing. If you want to use DHCP, it will do another thing. And then ultimately, it just has a simple combinator interface that says, given all of these configuration informations, just assemble them together, and then ultimately call the main function, and give it these device drivers. And you'll see the device drivers here are familiar. We have a console, a key value store, and HTTP, and we result in an executable unikernel that's a job. So all of this is type safe. If I tried to, for example, not supply a key value store, you would just get a type error. For example, if I try to assemble this thing and I miss out the key value store and I do the Mirage configure, it will just give you a type error. So in this case, it wants a key value store, but I've actually given it an HTTP, so it's just a normal type system error. So you can see when you're building sophisticated distributed systems, it is lovely to be able to just say, here's a DSL, give me this set of device drivers and just put them together in a type-safe way and then output the result you want. So one of the first use cases we're putting this to is in Zen itself. Because in Zen, the problem you have is you have a very complicated management tool stack, and you have to figure out exactly how to put all these things together. But you don't want to depend on Linux, because Linux is a thing you're trying to run on top of Zen. So ideally, you want to avoid this kind of management deadlock. And so a number of little web servers and so on, acting as little REST APIs, are all being put into Zen that are breaking it up into lots and lots of small components, and then using this kind of DSL methodology to assemble all the APIs and stuff together. So it is just a nice way to eat our own dog food as well and make sure that this stuff stays working. And just to make it even easier to use, you can also just, in the generated code, add extra OPAM packages or anything you need for your particular unikernel. So in this case, we can say, install the RE regular expression package and add that to OCaml find as well. And we're trying to make this simpler as we go along. So this gets pretty sophisticated. So I wanted to show you what we were working on the other day. So if we see here, we've actually built a TLS stack as well. I think I've just killed roll.ocaml.org. I have just killed roll.ocaml.org, but I killed it for a reason. And the reason is we've been eating our own dog food. This TLS tunnel here in Unix is a Unix version of a Mirage application that implements a completely type-safe version of stunnel or STUD, if you've used any of those before. And if you go to roll.ocaml.org now, you're actually connected to an OCaml TLS stack. And this TLS stack is built in exactly the same modular style, where rather than being a simple web infrastructure for implementing HTTP, it implements X509, ASN1, all of the low-level protocols for TLS, and cryptography layers, and finally the TLS protocol itself, and exposes them over a web interface and translates it to TCP. So if anyone connects from here, you can just see that it will just go on, and there's things being terminated and so on. Now, the reason this is important is because it means we can compile up a Mirage unikernel that is similar to the previous ones, except is now a fully standalone HTTPS unikernel as well. So we've been setting up a new bit of infrastructure on Mirage.io. Let me see if I can find this. I'm just going to SSH in and see if I can get this to work. So this is our little deployment box. And then we're now messing around with live infrastructure. So let me try not to kill it too much.
You guys actually wrote all those encryption libraries. You didn't just call out the sub C stuff like everybody else does.
No, yeah, so it's a great story there actually. So what happened is that we were sitting around in Cambridge, hanging out as usual, and I got a mail from these two chaps in Morocco, and they were on a beach in Morocco, and quite a lot of people get in touch and say they want to do something, and they said they want to rewrite TLS. So sure, go ahead and rewrite TLS. And 3 months later, sitting on a beach in Morocco, they had some of the most highly quality code I've ever seen. They'd just methodically gone through this and actually shipped us a patch that worked with TLS. And it had limitations, but it was pretty good. So at this point, obviously, we just stood up, paid attention, and invited them to come over at high speed. They left the beach in Morocco. And by the end of the year, this is in January, they were presenting at CCC with a full stack. And this is not only, it's not just a brute force implementation. It's structured in a really interesting way. The core of the TLS state machine is purely functional. So this means that for every single state transition in the protocol, it's built as a series of state in, state outs with no side effects. So just like you would in Haskell, for example. But then there's a effectful implementation, LWT, that decides exactly how to then start transmitting packets. There's then an effectful bit that starts taking in pseudo-random numbers. And then before you know, it's all kind of put together. But then there's also really nice little domain-specific languages. One, for example, for X509 certificate parsing in ASN1. So these are legendary in their difficulty to parse. It's just incredible. If you look at OpenSSL, that is the bit of OpenSSL that will just make you just leave the room. And it's just macros, and it's just extraordinarily hard to use. And so in the OCaml one, David Caliper, who wrote the ASN1, just has this beautiful GADT-based interpretation of the ASN1 grammar, where ASN1 is super general. Then you can define a grammar that restricts it to the protocol at hand. And so he's got a GADT that defines the grammar. And then you can apply that to the ASN1 implementation. It makes it more specific. And then you can start pulling out only the fields that are valid for that grammar. And so there's a bunch of blog posts at OpenMirage.org that describes this in more detail. But it's one of the first times I've actually seen a use of a GADT that wasn't, some weird academic thing like a typed interpreter or something, right? I mean, I love typed interpreter as much as the next person, but I kind of like seeing what they're for as well. And this is a great example where you want to interpret a protocol and you want to make it more and more specific as you go along. So, and the other interesting part of the stack is that because it's got this purely functional element to it, you can take that aside from the rest of the implementation and use it as a trace checker for OpenSSL as well. So I can say, given a bunch of packet traces for OpenSSL, you can then take the traces and say, well, would I do the same thing if I was run through me? And that's been really useful to check for behavioral uses and so on. So then they took it another step further. where we really wanted to test if this was any good or not. And so what they did was they created the Bitcoin Pinata. And this is the most fun we've had for a long time. Where here's the challenge. You take 10 Bitcoins, kindly donated by a Swedish ISP, who also gave us a server they didn't mind burning. And we put this Pinata up. And this Pinata has the 10 Bitcoins embedded in it. And it's also running the TLS stack as a unikernel. And what it does everything in its power to help you break it. So it'll give you a loopback connection. It'll replay all the packets to you, and so on and so forth. And you can connect to it. And if you can somehow get the private key, we'll give you the Bitcoins. And once you get the Bitcoins, we can't deny the fact, assuming you trade them, that the Bitcoins have been gone because it's a public ledger. And so this made it to the front page of Hacker News. There was tons of attacks. There was DDoSes. When there's DDoSes, the machine just went down, but it rebooted in 10 milliseconds because it just decided crashing was the best option. So it really was a real Pinata, right? It was just bouncing back after being DDoSed. It was awesome. At the end of it, so we've got a blog post coming out soon. Just a spoiler, the Bitcoins didn't get traded. But what we got out of it was just hundreds of thousands of traces that we've then been passing through our stack and using that to improve the implementation. And there's been tons of little refinements. TLS is just a massive protocol. There's been tons and tons of improvements to that. So now if, for example, you go to an SSL Labs one for, let's say we look at it for real world OCaml, and this is running, so we're pretty close. We get A- because it's using a SHA-1 signature. There's a few little bits and pieces, and we don't support ECC yet, which is a very useful part of SSL, but that's being developed right now. There's no fundamental reasons; it's just got to be built. But apart from that, it's just top notch. It's got a really good browser compatibility. It doesn't support some IE6. It's probably a good thing, but apart from that, it's in pretty good shape. So the nice thing about this is that we're trying to make it as simple as possible for people to actually use this thing. So the idea with this one is that we have the live website, and we're trying to create the infrastructure around this now, where you can just take a bunch of static HTML, and then you can figure out exactly how to just say, just take the logic, seal it up in unikernel, and just launch this in EC2 as quickly as possible. This automation doesn't exist yet, but it's kind of obvious to see how it could be done. It's just a matter of coding to all the right APIs. So if anyone in particular wants to get EC2 APIs, this would be just a heaven send, because it's just a set of APIs that get larger and larger and larger. Pretty much every language struggles with bindings unless they're officially supported by Amazon. But they publish kind of auto-generated schemas where you have to generate tons of code. This is actually kind of what Martin specializes in, auto-generation of tons of code. So, so if ever you need one, I'd love to hear about it, because then we could hook that into our infrastructure and just auto-launch EC2 APIs. But the other thing is the workflow has really benefited from Travis. So who's used Travis here for builds? All right, a few people. So Travis is really cool, right? Because let me just show what this thing does.
It's a CI suite, right?
It's a continuous integration suite. So if I take a non-incognito browser, and so what I'm going to do now, how do I not go incognito? How do I just say, let me just kill the whole thing, and it's just easier. So if I go to GitHub, and I go to Mirage WW, every time you send a pull request to this thing, it's built by a CI suite. So in this case, Tom Akazny just sent me the HTTPS support a few hours ago, and this thing is built. And when it's built, every single pull request is built by Travis, and we see here a bunch of deployment options. I'm sorry, it's a bit gray there, but the deployment options are basically different versions of OCaml and different backends from Mirage, so Unix and Zen, to make sure they all work. But then there's a version here that also deploys this thing to Git. So what it does is that given a build, I'll skip obviously all the build. It builds everything from scratch every time. It also, it doesn't do this for pull requests. Let me just find, it only does it for trunk build. So I'll just give you a trunk build here. And there we go. Let's load the log files. So what it's doing now is it is building Mirage WW, is building the unikernel. It's then recording everything it did to build the unikernel, the entire manifest of source code, and it pushes it back to Git. So here it's saying, given the Mirage deployment, given the all of the change sets involved, just clone a different repository, commit the unikernel to it, and push that away automatically. So now if I go to this this other one, GitHub Mirage WW deployment, you have a complete set of manifests of every single version of the website ever deployed, stored in GitHub. And there's quite a few there, right? So you can see we've been doing this for a few years now. So if I pick, for example, something from a few months ago, you can just use the SHA hash to trace back every single line of source code that's gone into this thing. Because clearly Unikernel has just been built through the OCaml compiler, and then with a little bit more scripting automation, you just need a few Git scripts and stuff. You know the configuration file that makes the entire Unikernel. This is the one I just showed you where it just gives it a bunch of addresses and netmasks and so on. And you have the actual deployed Unikernel. In this case, it's 3.8 megabytes in size. That's with debug symbols and all of the content of the website included into it, all the images and so on as well. So it's a nice way to deploy these things. So for example, if I wanted to have a log system, I could define a merge function that says, just don't ever have a merge conflict. Just order the merges by time. And you can write that as a simple OCaml function. So I wanted to show you a quick demo of what that looks like. So if I switch away from this, I'm going to go to Mirage now. I'm going to go to the Ermin. And we have a little wiki here. And we have a bunch of demos. So you can all do this by OPAM installing Ermin and following along if you want. So on the Mirage Ermin wiki demos, you can just OPAM install -t. What the -t does is install all of the test cases as well, so that you can build the examples. So what I'm going to do is I'm going to start this HTTP server in the background. Well, let me just find a screen with. Oh, wrong. Too many machines. All right, source git Mirage Ermin. Yep, and I've got the examples pre-built. So I'm going to start a web server in the background. And what this has done is that if I will just switch away and switch to temp ermin test. We now in here have a Git repository. It hasn't initialized yet. So what I can do is I can now open up a graph view, which is empty. And this is me connecting to the Ermin server and saying, just give me a view of whatever's in your Git repository. So I can do something very, very simple now. I can just say, give me a three-way merge where you have a log file and you want to merge a bunch of log files. So I will switch away to this and I will say, do a custom merge. So what's happened here is that this has just gone quite fast. It just said, given a few logs coming into the data store, each client has its own branch in Git. And you can merge them by just applying some merge logic, which essentially boils down to the newest one wins, and the other one goes behind it. And this has gone through and done all of the merges, and it's added a bunch of log files. If I switch to the view here now, what it's done is that it's taken a bunch of branches, in this case test and master, and it's gone through all of the clients, which are programmatically added merge files, and rendered them as a Git DAG instead. So what I can do now is I can, where are we? Temp ermin test. So now when I look at the Git log for my data store, this is Git. This is the Git command line being used, and it's simply adding log entries, adding log entries, adding log entries, and merging them as well. So what we've done is that we've programmatically used Git as a data store, and we can have the data in Git, and we can have the data in Ermin and go back and forth between them. So this is pretty nice because it means that we now have a bidirectional mapping between Git and OCaml code. And the examples are actually pretty straightforward. So if I look at a custom merge, for example, all we have to do is define in OCaml what it means to be a long entry. In this case, we have a pair of an integer and a string where the integer is time and the string is the contents. Define some comparison functions. Then I can just define a log file where the log file has a path, a way to pretty print it, and do some orderings. And the critical function that we add is basically this merge function where we say the way that you merge two branches in this log store is by just comparing the timestamps and just deciding which one wins. And so we just write that and we never have a merge conflict again. Consider in Git what would happen, right? You'd have to write a shell script. You'd have to parse the various text files. You'd have to make sure that you don't have any weird entries. And generally, you can never quite assure yourself you won't have a conflict. In this case, your OCaml code makes sure that this happens. So Ermin's also fairly scalable. We designed it to be a file store for virtual machines. So imagine what it looks like when we want to use this to do mergeable virtual machine deployments. So what I'm going to do is, we have a simple demo. And I will just switch to this. And I'm sorry, I didn't show you this before. This is showing the full sequence of operations in the story. You can see in our distributed system all of the merges that happen to make that. Even the simple example is fairly complicated. So what we're going to do is, I'll switch to, I'm back here again. So we have this deployment where I'm going to provision a virtual machine. And so what's happened here is that we've provisioned an Ubuntu virtual machine. And it's got a file system that is a normal Linux file system that has etc and bin and man path and so on. And this is exactly the sort of thing you do in Docker, right? But then we will go off and configure some software. This is sysadmin just connecting to it and installing some software. And so what's happening now is that we've logged in. We're making a bunch of changes to the file system, which modifying resolve.conf and so on and so forth. And you can see that the user who connected to Ermin was Bob the sysadmin, because we are keeping track of who in the file store is changing things. And we now have multiple branches. We know that the upstream branch is the original Ubuntu. And we know the development branch is what Bob the sysadmin has done. And that's a Git store based off Bob the sysadmin. So now we can then go off and say, let's say someone attacks poor Bob. And when someone attacks poor Bob, what will happen is that someone makes a remote connection in. The Git tree will start changing because we're making remote connections and we're starting to add more and more attack vectors. But because we're keeping track of our provenance, we know exactly which bits and pieces went into each one of these branches. So we know that our production tree has now diverged from our development tree. And in this case, someone has run gcc -c and installed an attack binary. And we can diff exactly what's changed. And then all we have to do to revert that is by saying that we just simply want to make sure that dev and prod are reconciled and just rebase the entire file system. So Ermin is the sort of library where we can export a fused file system to a virtual machine and make sure that all of these kind of policies can be enforced. So this is just a nice way of tracking provenance. So we originally started this as a way of doing this kind of virtual machine tracking, but Ermin has now become the default store for Unikernels. So instead of having a POSIX file system and all of the complexities around it, Unikernels coordinate simply by doing git reads and writes at the same time. So one of the more complicated uses for this has been in Zen again, where the Zen data store has been rewritten to support the use of Ermin. So every operation in Zen when booting a virtual machine can be tracked in a Git store. So when it comes to debugging something, in the old days, you got a million hosts deployed on Amazon or Rackspace or somewhere. And now in the future, we're hoping that you can simply clone the administration database to customer support, and they can see all of the individual operations that happened. This obviously takes up a lot of disk space, but it's less disk space than sending a human being over there and trying to debug gigabytes of log files. We just maintain all the orderings between operations. So it's exciting that we're kind of Unikernels give you a chance to rebuild clean slate protocols and give you a chance to rebuild the world in the way you want to think about it, instead of the way that the world forces you to think about problems because you're using old legacy APIs. And then you can still map those onto other systems. So if you go through the demos, there's tons of other demos as well. Ermin is still under heavy development, so it's being used by a bunch of people for interesting problems. But now is the time to start thinking of interesting use cases and data structures. One of the slightly crazier things that's happened is Thomas Leonard, who started working with Thomas, compiled the whole of Ermin, the whole of the data store to JavaScript using JS of OCaml. And then all he wanted was a to-do app. It always starts with something innocuous. But now the to-do app is an entire JavaScript framework that version controls all UI operations in the browser, supports cross-browser sync, and generally persists everything using the Ermin store. So if you want a to-do app that is Git tracked, this is Mirage running in the browser effectively. So it's taken a bunch of the Mirage libraries. And for example, I can launch another QKeeper thing in another browser. So now I have two tabs running in the browser. And then I can start making changes in one. I can change, for example, a Wikipedia page, and this immediately reflects in the other one. If we can slow things down, it's possible to, in different tabs and so on, to make pretty fundamental changes and result in merge conflicts. So what's happening here is that I went through one browser and finished a task, then the other browser tab and changed its due time, and there's a merge within the browser. And if you look at the developer tools around this, you'll see that within the browser, it's using local storage and IndexedDB to map the Git concepts into local storage, and using that as a nice abstraction to form a Git-like store in the browser. But then, of course, this entire thing can be exported to a server running Ermin, where you then surface it into Git. So we're essentially programming Git both in the browser and back and forth again. So this is a really interesting way to do reactive programming with persistence. So you can say that I just want to program against Ermin, use that as my data store, and then have Mirage decide to surface this in JavaScript or in a unikernel or under Unix. So we're still exploring the edges of the JS for OCaml integration, but it's just a really exciting time to be compiling in JavaScript and having access to all these tools. To make it possible, we've had to use the pure OCaml implementation of Git, a pure OCaml implementation of compression, and all of these just compile into the browser. And if there is a version available for JavaScript, we just use the native versions. So JSON is a good example where you just try to use the native parsers in the browser way faster, but then you use a similar interface and you just compile it into Unix and do all the parsing yourself. So the module system in OCaml has been very, very useful to make that happen. So has anyone here tried Ermin, by the way? Because we received a bunch of emails from California, so I was kind of wondering who that was. I see a few people nodding, but no one's really used it. We haven't really released Ermin as a 1.0 because the state it's in right now is that the Git implementation is super, super rock solid. Well, as far as there are not many known bugs. And we're building the data structures around it as well. So one thing we'd be really interested in are use cases that people might have for this kind of infrastructure. In particular, you can think of this as a programmable Merkle tree, which is the thing that Bitcoin's based on. So because Git is essentially a sequence of hashes, it means that you have a cryptographic witness for whenever someone does something. If I commit something to Ermin and I push it to the outside world, then it's very hard to repudiate that because someone else has got a sequence of hashes and they will disagree with you if you try to change your mind, and you're forced to merge with them. So it's particularly interesting for logging, where you want to have signed immutable logging and kind of put that together. So it's likely we'll release this into OPAM as a bunch of utility commands you can use for logging for things like key signing, for example, where you just want to have an immutable persistent store that keeps increasing. The big feature that we have to add before a stable release is garbage collection. So garbage collection in this world becomes rebasing your Git repository every so often. And so you have to figure out exactly when the right time to rebase is. Because in the case of logging, you don't want to keep every individual commit for every individual log. After a year, you might want to discard that and rebase it into just a log file and save a bunch of space. But equally, storage keeps growing, so why not just store everything for a long time? There's no fundamental reason why you shouldn't store everything. But we just want to give people the option, for example, on a browser or a mobile phone, to garbage collect these things. And if anyone wants to play around with this, it's kind of a nice way to just learn more about browser programming as well. We found just a ton of bugs in Safari, in particular, from IndexedDB, which Thomas Leonard is fixed by random sleeps and stuff. There's just no way around it. But there are obviously many people in this room probably better at browser programming than us. So the Mirage list has a bunch of discussions about Zen device drivers and JavaScript right now, so it's a bit of a weird cognitive dissonance. But they're both equally interesting. So anyone who joins will probably learn something, even though they might not have wanted to about JavaScript. So I just wanted to give you that really quick view. And I just want to conclude with one really cool demo that Magnus just gave. So let me explain to you really quickly what this thing is. And we presented this at Usenix this morning at NSDI. And I'm obviously not going to go to the whole slide deck. I just wanted to give you a sense of what we're doing with these ARM boards. And the idea behind the ARM boards is that we want to have virtualization at the edge. We want virtualization in everything that permeates the environment because the problem is just security and latency, right? If I use Siri here right now to say, hey Siri, how far is it to Esper? I don't know, it might come through, disconnect to the Wi-Fi. I mean, this is unacceptable latency, right? But it's just taking forever. That's about 4 seconds. 4 very awkward seconds. So ideally, we would just connect directly to our local infrastructure and just ask it a question and get instantaneous response time. That's what the science fiction movies promised. So ideally, to do that, we want to have multi-tenant devices all around the environment and with extreme security. So we don't want to deploy Linux containers. And there's just this classic quote from an embedded systems conference just last week. White Quark just tweeted this. So these cars have infotainment systems that are by nature open and internet connected, and thus open to outside attacks, while other mission-critical driving instrument systems cannot afford to be compromised. Makes sense. But to save a few $1 million, they install the two systems on the same embedded device in the same privileged separation space in the same shared network. So suddenly your car's infotainment system can install a random app that disables your ABS. And so DARPA funded a huge program called HACMS, all about building drones. And one of the demonstrations they had was a hacker could wirelessly take over a car and force your seatbelt to stay attached. So a driver could have their ABS turned off and their seatbelt forcibly attached, and it's a bit of a nightmare scenario. And we've heard the same things through aeroplanes and so on and so forth. So it's clear that if virtualization is going to happen, you want it to happen in your car and your airplane, because that's where you really need this kind of security. But the people here are kind of not very minded towards anything other than cost savings until legislation happens. So we wanted to figure out, can we use these unikernels to boot up services really, really fast and with equivalent resource usage to embedded to systems such as containers? And the answer, in a nutshell, is yes. Thankfully, otherwise I wouldn't actually be in California at the moment. And what we did a bunch of work. We ported unikernels to Zen ARM, and this is this little 39-pound device that you see here. And we built a new tool stack. This is apparently Magnus's work that is designed to be low latency on ARM and can boot unikernels and respond to service traffic in response to DNS. So the way it works is, let me just show you, just skip through this. So what we have is this. We have a client in this room, and the client makes a DNS request. And the DNS request, it goes to this little box. And this box is running this thing called Jitsu, which is a just-in-time summoning of unikernels daemon. And what that does is that in response to that, it boots up a virtual machine, right, which takes about 10 milliseconds. The problem is I'm only 1 millisecond away from this device. So what happens next is that this TCP connection will come from my client because it's got a DNS response immediately. And unfortunately, my unikernel hasn't quite finished booting. It's 10 milliseconds. It's pretty fast, but it's not instantaneous. And so we observe packet loss, which is, we don't want that, right? We want our instantaneous response. So what we do is that we spin up another unikernel that has already been running, and this records the TCP traffic that's going into the system, and it waits for the unikernel to be brought up, for its networking to be brought up. And here we're talking about milliseconds of time. So everything is being parallelized and happening at the same time. And then, as soon as the unikernel is active and woken up, we can replay all of the buffered up TCP connections and respond. So this client has no idea what all the crazy stuff going on, but it's in a very race-free way. It's just made an HTTP request, it's sent the SYN ACK, and it's got the HTTP response back. So it means that we can actually just spin up unikernels that live for seconds at a time, kind of like a content delivery network, except that it's actually spinning a virtual machine. So you can actually have these tiny little dust clouds that are running all over your ARM devices with full Zen isolation, running as unikernels. So it's a really interesting way to build embedded systems. There's obviously a lot of work to be done from here to production deployments, but a lot of the hard work around the Zen tool stack has been done. So if I show you this, I'm actually logged into the QB board. So this is the board in front of me. It's running a domain 0. I can, for example, cd into Git. I can pull up, for example, this slide deck. This is all of the slides you see are written in Mirage. I can cd a source directory. I can look at my, I won't bother building it because the ARM box is quite slow, but this is just a normal Zen configuration file. I can do xl create -c live.xl, and this is spinning up the slide deck. This has got an IP address of 192.168.3.2.31. I can go to that in the browser, and we've just got a local service running here as well. So, and Magnus, do you want to, just to wrap up, do you want to show the Senjutsu demo? So we have a screencast here because it's a bit awkward to set up DNS and stuff, but why don't you come up and...
Yeah, so we recorded this as a screencast just in case something broke at the conference. But what this shows is 3 SSH sessions, 3 keyboards. And in the lower terminal, we're going to show all the virtual machines running. Oh, sorry. I think it's...
No, go for it. I'll just stand here.
Okay. And here we can see the virtual machines that we have registered. They are all shut down at the moment. Oh, okay. If we can get the... So first, I'm going to just start a normal web server unikernel using Jitsu. So Jitsu acts as a DNS server. It will serve the domain Jitsu.io, and whenever that domain is resolved, it will give the IP address that's shown there, and it will start www, and after a certain timeout, it will destroy the VM if there's no request within a certain time interval. And unknown DNS request will be forwarded to Google's DNS server, 8888. So now Jitsu is running. And now if we ping Jitsu.io, we should see down here that www is booted automatically, and we get a ping reply.
This is a list of virtual machines on
the
system.
And now if we destroy the VM, we can also try to telnet to port 80. And then we can see that it's connecting, and we can download the index HTML file, which contains the Hello Mirage World example from earlier. But you may have noticed that when we tried to telnet to the virtual machine, there was an initial delay after we resolved the domain of about 1 second. And that was because we missed the first SYN. So if we try that again, we can see the delay here. Then we're connected. So to compensate for that, we are going to use the Senjitsu unikernel. And the Senjitsu unikernel is going to capture all the incoming SYN traffic on the send bridge, and it will store those SYN packets in SendStore, as Anil explained. And when a unikernel then boots, it will look for SYN packets in SendStore, deserialize them, and inject them into the Mirage TCP IP stack. And for this, we're going to use Senjitsu app, which is basically the same as the web server. It's a unikernel that listens to port 80, but it has been compiled with a TCP IP stack with Senjitsu support. So we're restarting Jitsu. And now if we telnet to Jitsu.io, we should be able to connect without any delay. Let's see, yeah, Senjitsu is running. And there we were connected right away. And what happened was that Senjitsu now stored the SYN and held on to the SYN until the unikernel had booted, which was maybe 50 or 100 milliseconds later, and then passed the SYN over to the unikernel. So here we can also see what the SYN looked like when it was serialized and put into SendStore. So here's the SYN data. So yeah, so using this, we can actually spin up and down unikernels automatically on the QB board. So even though we're not able to run more than maybe 30 or 40 unikernels at the same time, we can use the resources more efficiently by just starting the services that we need when we did. Cool.
So I just want to show you some of the cool tricks we can do. Obviously, there's been a lot of investment in building Mirage and building these libraries. But now we're reaping the rewards because we can suddenly use these libraries a bit like off-the-shelf components. Think of a crazy plan involving infrastructure and just program those directly. So you don't need to struggle with configuring DSP servers and dealing with all the little configuration stuff. Well, instead you just have to struggle with your OCaml libraries. But that's a struggle that we enjoy because it's a struggle we enjoy because it's a normalized form of configuration because you configure everything through a normal programming language. And you can manipulate all of the totality of your infrastructure through one particular DSL. So it's a nice way of programming. So that's been a bit of a whirlwind tour of Mirage. I didn't obviously intend to deep dive. I wanted to give you a sense of where some of the innovations are and what's going on. It's becoming a viable way to build real infrastructure. So, for example, if I go to my web browser again, as of this morning, we now have a new Mirage.io, which is running a full TLS web server. And our focus right now is essentially just making this stuff easy to use for other people to deploy. There's been quite a lot of demand from people who just want to use this stuff now. So obviously, this has been going on for a while. And so the whole team is essentially building QA infrastructure, running this stuff through stress generation, building things like the Bitcoin Pinata, gathering your feedback. And we're aiming towards Mirage 3.0 release as soon as we feel it's past release toll gates. So what we need now are essentially users who are lead users who are familiar with OCaml and are interested in learning this stuff and thinking of interesting little use cases that we can help you deploy and kind of put together. So it'll definitely not be pain-free because there's just a lot of usability things that we're just clearing up, the usual kind of stuff. But it's exciting because we're aligning this with a lot of work we're doing on the OCaml ecosystem as well. So we've been doing a bunch of work in OPAM. Over the summertime, we're working on the OCaml platform, which is a set of tried and tested tools we can release that are nice and modular and simple, all based on OPAM, that help with build and doc and testing and all of the life cycle of things you need to do, because we need this as major OCaml users as part of our MirageOS world as well. So it's lovely to be able to have the opportunity to work on the infrastructure, because that infrastructure just makes my own hacking time more efficient by for example, letting me use OPAM in MirageOS and releasing 100 libraries into that ecosystem as well. And it gives us the opportunity to use all of your libraries as well. So I was just chatting with you about Captain Proto bindings, which we want to use as our inter-unikernel API, and it's just lovely that I didn't have to build those bindings, right? It could just be done and used and published in OPAM as well. So again, if there's any bit of the OCaml platform that you particularly have a burning need to see, we have a platform mailing list on lists.ocaml.org, and just do feel free to send your particular use cases and exactly what you want to see from your workflows for your companies or your personal hobby hacking, and we can make sure that's all integrated into the platform. The platform is very much intended not to be prescriptive, but to make sure that every single company that's using OCaml has the ability to program their own workflow in the way that they need to work. So if you need closed builds behind a firewall with no net access, that's fine. If you want to publish to OPAM and have it do the testing for you, that's fine too, or something in between. So we have obviously people like Jane Street and Citrix and Facebook and Esper and all of the companies who are using OCaml in a serious way, and the platform just intended to support them, and at the same time help efforts like MirageOS as well. So, but I think I'm pretty much done talking. If there's any questions, or otherwise we can just get back to eating all that lovely food over there. So. Ewan.
One of the things you kind of glossed over at the beginning even was that because OCaml is type safe, the system is set for type safe, you can align a lot of the checks between kernel and user space that would be traditional in the Linux kernel.
Yep.
How close are you to that?
Could you repeat the question?
Yeah, that's right. So Ewan Meller there from Tippett is asking, originally the plan was to use the static type checking facilities in OCaml to remove the need for a kernel user space divide. So we've been living the dream for 4 years already. So the unikernels that you see here are single address space virtual machines that have no kernel and user space divide. So when you're compiling up one of those Zen unikernels, it's running in one address space. And a lot of the type checks, for example, permissions accesses, bounds checks. Sorry, bounds checks are done dynamically, but some of the bounds checks can be alighted through the type system. But the majority of things are just pure OCaml code. There's very, very little C code there. So you don't have to be a kernel programmer to benefit from this. You simply use Mirage. It takes care of making sure that all the address space separation checks are done for you, and it outputs a unikernel that you can just use. That makes sense. So yeah, crucially, the intersection of functional programmers and kernel programmers tends to be quite small. And with this world, all of you can become kernel programmers because you just build one of those little unikernels, and that is a specialized kernel. It's as if you built a Cisco, iOS or a NetApp Waffle type appliance. It's just you happen to be building it much more simply now, so you're getting those benefits. Is anyone here actually a kernel programmer and a functional programmer? Out of curiosity. There you go. Yeah, perfect. You can help us debug the kernel bits. Hi.
Can you give a couple of examples of practical applications of maybe cool research projects that specifically benefit from fast boot times and isolation?
Right, from fast boot times and isolation. One of the big drivers for us was personal clouds. So we want the ability to have these home devices running a Raspberry Pi, storing all your personal data on there. And that's a really good use of multi-tenancy and isolation, because typically with this stuff, you don't want to be wasting power all the time in your home. You don't want a billion devices all sitting there serving services. So the model is that you don't really need to access your photographs that often, but when you do, you want to have them private, and you want them nearby you because it's quite a lot of data, say a terabyte of photographs. And so Jitsu was specifically built as part of a project we're doing called user-centered networking, where you give every individual on the planet their own domain names, because you can own your own domain name. And then from there, it forms a root of trust for applications such as your personal email, your personal photo sharing, and then building a multi-tenant set of distributed devices that can pull that off. Now, I built a prototype that did this in about 2009, just for my personal use, and I just didn't trust it. I ran an app engine in Google, and when you start putting your own personal data at scale there, it just takes one bug in the code to mess everything up. So we spent the last few years, efforts like Mirage are improving the application stack, and we've also got other efforts in storage, such as Ermin, which is you're just tracking everything so you know when something goes wrong. And the first step to being able to forget your data is to remember where it is. And Ermin is a data structure that never forgets. So at least when it comes to a distributed system, you know exactly what you need to go out and blow up in order to destroy all that data. And finally, it's also extremely useful for microservices, because if you're just dealing with scaling and you're turning things on and off and so on all the time, then dealing with flash traffic is a really, really nice use for this. Because imagine you're running on a PaaS and you want the ability to quickly spin up something, then you want to have this kind of model where you can just have services that are your code running, but without having any kind of isolation problems because you're running in a PaaS. Typically, right now, you have a choice between infrastructure as a service, where you have your own virtual machine, and a PaaS like Heroku, where you're not really sure what the isolation properties are. So this way, you can start putting more and more mission-critical code onto and get the benefits of a PaaS-style API without having to worry so much about isolation and multi-tenancy as well. Yeah, the question is if you need to scale in terms of CPU. Well, most services are more than just CPU. So a good example is if I have one of these web servers and I want to turn it into 2 web servers, I need to spin up a second virtual machine, but I also need to spin up a load balancer. And so this means that there's this kind of gang scheduling of multiple virtual machines that all need to be coordinated and spun up. But then you also have existing connections to this web server. So just the act of splitting up one web server into 2 requires 3 virtual machines to be spun up. 2 new web servers, a load balancer, and then this virtual machine needs to finish its connections and spin down. So coordinating all this stuff at low latency is so much easier. If you're doing this where it takes anything from 30 seconds to a minute, then you just can't react in a fast way. Magnus actually built another thing where he had a unikernel per URL. So imagine you have a REST service where you want to have a whole bunch of dependencies for writes because you have a put request, and a whole different set of dependencies for read requests. In this world, we can actually spin up a unikernel just for a write. And that can be isolated from all of the reads. And that can have things like session keys and all the things you need to do a write. So we can actually build very, very fine-grained unikernels depending on your level of paranoia. Now, the goal here is to make this paranoia invisible. It should just work, right? So when you build this stuff by default, it should just have security. It should just permeate everything. And we just want to make security so cheap that you can just do that. Because people don't really care about security when you're in the business of deadlines and running code. So a lot of this technology should just fade away into the background and just work as part of the PaaS. And if isolation costs you nothing, then just take it and don't do all the leaky abstractions. It isn't say, so yeah, you're saying Heartbleed. I think Bruce Schneider said it hit 18% of all internet web servers. The irony with Heartbleed, an SSL bug, is that by running an encrypted protocol, you made your system more insecure than running Telnet. Because with Telnet, only a snooper can see your traffic. With Heartbleed, they can see all of your memory. So it's just taken us multiple steps backwards. Shell shock is an interesting one as well, because shell shock is the bash issues. And the estimates are the shell shock will never be fixed in this generation, because there are so many billions of embedded devices with bash embedded in there that are vulnerable, and we just have lost track of what's going on. They will never be fixed, right? And they're probably in very, very mission-critical things. Stuxnet is an example of nuclear power plants being taken out, cyber-physical infrastructure. So with this stuff, the idea is you can just build infrastructure that is isolated and